So for this final part of the Advanced Experimental Techniques lectures on noise, I want to go talk a little bit about actually some points that when measuring the noise has turned out to be the interesting thing to go and do. So we've talked about situations in which we want to get rid of the noise because it's interfering with our known signal, but there are also occasions on which the noise itself can be interesting or useful. Okay, so I'm going to talk actually give a few examples. So one where it's actually caught some academic misconduct cases by paying attention to what the noise was doing, but also ones where measuring the noise was in itself the useful thing to go and do. And finally, we'll finish by looking at a situation in which introducing noise into your measurement can actually help you. So there's a very famous case in the field of organic superconducting materials and organic electronics, which occurred at the start of the millennium. And so this was a case in which a relatively junior, well, relatively junior, a young scientist at the time, Jan Hendrik Schön, was accused of perpetrating a massive scientific fraud. So Schön was working in superconductivity of C60 materials, doped C60 materials, and of electric field control of superconductivity. He was working in the Bell Labs, but as is the way with lots of these things, he was also involved in collaborations with many groups across the world. He'd made several interesting breakthroughs in the field of electric field control of superconductors and organic superconducting materials. And by 2001, at the age of only 30, he was authoring basically a new paper almost every week. And this wasn't just in some random journal. These were papers in Nature and Science and Physical Review Letters and the really most prestigious journals. And it pretty much seemed that everything he touched turned into a golden paper. Huge volume of papers coming out, and many people were really keen to collaborate with him because they reckoned that he was the magic pixie dust that would turn whatever their material was into some fantastic paper. So very, very happy to go and provide him with materials, very, very happy to be on his papers. And then there was a problem, because on one of his papers, which wasn't in fact going to be published particularly in a leading journal, it had been sent to a young postdoc to peer review. And she was quite eagle-eyed and spotted that one of his figures in this paper seemed to be identical to one of the figures in one of his other papers. And so she rejected his paper on the grounds that the figures were the same. The problem was that in replying to this, he wasn't really able to give a satisfactory account of why those figures were the same, because they were purported to be of completely different materials. It wasn't just that he'd accidentally copied the wrong figure file into the paper, which is what he at first claimed, because the formatting of the figure was subtly different. I mean, it had been replotted, but it was the same data, and it was labeled as though it was different data and different materials, but it was in fact the same data. And the peer reviewer had spotted this. And so that gradually got people starting to go and look at exactly what was going on. And then they started looking at his data, and they couldn't quite believe how good his data was. So he'd published, in this case, showing a couple of examples of figures of the temperature and gate dependence of his material, which was a doped C60 type of material, and in this case they were looking at the resistivity. And then if you replotted his data in order to look at kind of the activation energies of what was going on, an Arrhenius plot, then this fitted the Arrhenius model not just quite well, but perfectly over 25 orders of magnitude. And then they looked in more detail at this, and they realized that in some of his figures, where he did have what looked like experimental noise, if they took the spectrum of that noise, then it wasn't fitting what you'd expect from either Johnson noise or shot noise. In fact, it was fitting some other mathematical function. it just wasn't plausible. It was the wrong type of noise. And so it became rather obvious that he'd just simply been inventing his data. So this analysis showing that either the one case is where he didn't have any noise at all, and where you looked at the resistances of the materials and the temperatures he were operating at, and you went, no, you should be able to see the Johnson noise in this measurement, and it wasn't there. So how had he got rid of Johnson noise? And in other cases where he did have noise, but it was too perfectly the wrong mathematical function, it was clear that this was fraudulent. So in fact, he was found to have fabricated data for an absolutely crazy number of papers, and these were being published, as I say, in the most prestigious possible journals. So his papers were withdrawn. He acknowledged some level of scientific misconduct. I mean, on the way, he alleged that he hadn't been able to keep the original data because the computer he was using at Bell Labs didn't have a big enough hard disk drive, which, you know, frankly, given he was publishing Nature papers and science papers at the rate he was, how he couldn't go and persuade them to give him a bigger computer was just not credible. His collaborators and the bosses at Bell Labs were cleared of misconduct, but it's very clear that they didn't ask enough questions about the papers that were being written. That they weren't being sufficiently skeptical. They just went, well, he's just got a paper for me in this prestigious journal, it must be all right. So it's actually led to a whole series of changes in the field. So what we've ended up learning about this as well, I mean, first of all, that nobody should be beyond scrutiny, no matter how obviously successful they are, no matter how prestigious their funding is or their reputation. You still have to go and be skeptical about data. And I think particularly this is true in the modern world, where the most successful labs tend to be very, very large, and often the person doing the research and even writing the paper is not as tightly supervised as you might like to hope. If something sounds to be too good to be true, then it almost certainly is too good to be true. And perfect data just doesn't happen. Real systems are never perfect. And so if you have perfect data, it's probably simulated data. And I'd say one of the other changes that's happened is that it's now got a lot stricter, or the journal's got a lot stricter about ensuring that all the authors on a paper know that they're an author on a paper, and they are often explicitly required to say, to acknowledge that they've read the paper and understood the paper and been part of it. And it's now become one of the great social faux pas of being a scientist, is to put someone on one of your papers without asking them first. It's happened to me a couple of times, and I've not been very pleased about it. And when it's happened, I had words with whoever did its boss and said, you can't do that, because when you put your name on a scientific paper, you're kind of putting your good reputation to stand by the work. But you know, fraud still goes on in many ways. So there's a couple of examples here, and again, you know, we see cases occasionally of people trying to get away with either stealing data or stealing, some cases, whole papers. And you suddenly find that the text of an entire paper has been reproduced from somewhere else, just with a couple of new figures put in its place. So this is kind of a bit of the ethics, which comes out of simply knowing what's going on with your noise and what to expect. But Schoen would never have got picked up if it hadn't been for an eagle eye reviewer, and it hadn't been for people actually looking in detail at his data and about the particular noise of his data. Okay, so I talked in the earlier lecture about the early experiment in radio astronomy to go and see that the galactic center had an active radio source in it. And again, another early experiment involving microwaves. Initial experiment showed that there was some kind of variation in the signal that was being expected, and an unexpected fluctuation, unexpected what looked like noise. So despite an initial assumption that this was a guano-related noise, by persevering and working carefully to analyze where the noise was coming from and its characteristics, what they're able to show is that their directional microwave antenna experiment was in fact picking up a genuine fluctuation in the microwave background of the sky. And so what we were looking for then is trying to test everything they could work out about the noise. So they figured out, first of all, that it didn't depend on the receiver temperature. They were using liquid helium to go and cool their receiver down to make sure that if it was very, very cold, the noise didn't get less. So that was proving it wasn't Johnson noise in the detector. It was directional, but they checked it being directional against all the signal sources on the Earth and in the solar system. And no, it was consistently directional to the sky. They also were able to show that they were outside the point where the 1 over F noise was a problem. So that was not generic 1 over F radio interference because of the frequency in which they were able to detect it. And then finally, you did the test to make sure that there were no other radio sources that could be bouncing signals around the atmosphere or anywhere else that could go and lead to this unexpected source. And sometimes that can be very, very difficult to work out. And sometimes, of course, it could be that you're not going to necessarily be told if there's a radio source. And you might, for example, have to make some discrete inquiries with the Ministry of Defence to make sure there's no unexpected spy satellite that could possibly be interfering with your scientific experiment. Whether or not they tell you the right answer is another question. But in this case, this directional horn antenna experiment had picked up a real signal. And of course, what we were able to later go and show by doing satellite missions is that this unexpected signal in the sky was in fact the variation due to the cosmic microwave background. Okay, so as a final example of having sort of worked your way in and try to make sure you've understood your noise and eliminate all things, we're going to look at a kind of fun case where, in fact, having noise in your signal may not make things worse, and even more than that, you might actually add noise to your measurement in order to get a better measurement. So in this case, imagine a digitization system where we can digitize into levels 1, 2, 3, and 4, which are the dark black lines. And basically, every time we cross one of the dotted grey lines, that will switch us from digitizing to the black line below it to the black line above it. So we can see with this blue, the blue is our signal that we're trying to measure. Then what we would actually go and measure with this would be the red signal. So we'd stay on the level 1 until the blue line crosses the threshold between 1 and 2, whereupon we'd measure 2. But then when the signal does another step up to be just above 2, we still don't measure anything more than 2 because we've not crossed the threshold. It's only when we cross the threshold between 2 and 3 that we'll switch to measuring 3. So we're measuring now the red signal is what we actually measure when the blue signal is what we were trying to see. The problem is now is we've missed that middle step. So rather than seeing that there are 3 steps there, we think there are only 2 steps because we miss altogether the middle step. So now think what happens if we were to add between 0 and 0.5 units of random noise, so the blue spikes. So we randomly adjust the amplitude of our signal between somewhere between plus or minus 0.5 of signal. So now when we go and do the measurement, what we'll see is that on that first step, every time we're below the dotted line between the 1 and 2, we're going to measure a red number, a red point. And then every time we happen to be above it, we're going to measure a green point. And what we see is that out of those 16 measurements that we've done, 12 of them were red and 4 of them were green. So in other words, what we're going to measure is that 12 times we're going to measure 1 and 4 times we're going to measure 2. And if you work out that average, it's going to work out that you're going to measure 1 1/4, which on average is in fact the right number for the height of that particular step. And then if we repeat the process again on the second step, so we add between plus or minus 0.5 units of random noise, and what you see is that 12 times out of 16 we're going to measure a green, so we're going to measure 2, and then 4 times out of 16 we're going to measure the red, we're going to measure a 1. And again, if you now work out the average again, you're going to have an average of 1 3/4, which is indeed the value of the signal there. So what we've done is we've added random noise, and we've actually recovered, by then averaging it, we're actually able to recover a measurement of that additional step. We're able to measure less than 1 digitization level. So in fact, we've improved the resolution of our measurement just by adding noise to the measurement. Of course, the question is, what have we actually managed to, how have we managed to go and do this? I mean, there's no such thing as a free lunch. So the question you might want to ask yourself is, what have you actually given up in order to go and improve this resolution like this? How's this got better? Okay, so then to conclude this series of lectures on noise, so first of all, the thing you want to appreciate is that all noise has a physical source. It's not just anything as a random noise. Random noise is not really a thing. Random noise is a result of particular physical processes that you can understand. Noise can tell you an awful lot about your system. So, for example, if you measure the Johnson noise, you can actually get a very sensitive measure of the temperature. So measuring the noise you get on a high resistance will tell you what temperature that resistor is at. And in fact, you can just sit there and just measure the voltage without any current. And by measuring the RMS voltage signal you have a temperature sensor that's not in fact dissipating any power at all. You can do the same with shot noise to measure characteristics of your system. And then, although you can do various things to go and control that noise and get rid of it, if you have absolutely no noise at all, you want to be really suspicious about what's going on. And often, in fact, the noise itself can tell you an interesting thing about what's going on. You can actually understand the physics of your system by analyzing what the noise is doing.